Hi everyone, and welcome to another seminar of mathematics and high energy physics at Physics Latam. Today we have the honor of having Martijn Kool giving us a talk. Kool obtained his PhD under the supervision of Dominic Joyce at Oxford in 2010. He spent from 2010 to 2013 as a research associate to Imperial College, and from 2013 to 2014 as a postdoctoral fellow at the University of British Columbia. In 2015, he started working as an assistant professor at Utrecht University and was awarded with the Marie Curie Individual Fellowship. Martijn Kool works on modular spaces of geometric objects, on algebraic varieties, and associated invariants such as Euler characteristic. He will be talking today about this, Vafa-Witten invariants, and Donaldson-Thomas invariants. He also studied generating functions of such invariants on particular geometries such as toric varieties, local surfaces, and elliptic vibrations. These generating functions are related to combinatorics, classical enumerative geometry, and modular forms. He also works on several influential mathematics publications, and his work has been very fundamental in enumerative geometry and also in algebraic geometry. So we are really happy to have him with us today. Thank you very much for accepting our invitation.
Okay, thanks Daniel for the kind invitation. So yes, I'll be talking about Euler characteristics on moduli spaces of sheaves. So yeah, please interrupt me if you can't hear what I'm saying, or if I should explain something a second time. Please ask questions and yeah, do interrupt me if something is not clear. Also, I have prepared quite a few slides, but we're not under any time pressure. I'll just see how far I get. I'd rather go slowly through it than go quick. So, of course, it's a little challenging to talk about this topic without some basis in algebraic geometry. So I will have to assume a little bit of background, well, quite a bit of background of chapters 2 and 3 of Hartshorne. So I'm assuming some familiarity with sheaves, although often varieties are enough. We'll always be working over the complex numbers, by the way. I will also need the notion of a sheaf, sheaves of abelian groups, sheaves of modules, and some sheaf cohomology will also play a role. And also maybe some parts are more about giving you a flavor of the topic. So I can't in this amount of time really go to all the fundamentals. So sometimes I try to just give a flavor of the topic. But one thing that I want to stress is it starts all quite abstract. A book like Hartshorne looks all very abstract, but you'll see that a lot of it is actually very computational. And this is one reason it's very useful for physics, because in the end, algebraic geometry is about polynomials. So it's very suitable for calculations. All right, so let's start with some preparations. So for now, let X just be a variety over complex numbers. So some space cut out by polynomial equations. I'll denote by mod X the category of sheaves of OX modules. So over each open subset, you have a OXU module. And by co-X, I mean those sheaves that are coherent. So the first thing I want to talk about is the gluing of sheaves, which is actually an exercise in Hartshorne. So in this exercise, you're given a variety. He does it more generally over a scheme, but let's say we have a variety and some open cover, open subsets in the Zariski topology. Then let's first introduce some notation. By Uij, I mean the intersection of the open subset Ui and Uj. And let's say on each of these open subsets, we have a sheaf Fi, a sheaf of modules, let's say. And let's say we can connect these sheaves as follows. So if we are on a double overlap, Uij, well, on the one hand, we have Fi living on Ui, so we can restrict it to the intersection. We also have Fj living on Uj, so we can restrict it to the intersection. And let's assume we have an isomorphism between these. So we want to identify those pieces. So what we want to do is we want to glue these Fi's to a global sheaf F on X. So if this can be achieved if these phi ij's satisfy some properties. So phi ii should be the identity, phi ji should be phi ij inverse, and then there is this interesting, what's called co-cycle identity. On the triple intersection uijk, if you first go from fi to fj, and then from fj to fk, and then back from fk to fi, you should have the identity. Well, what Hartson tells you is whenever you have this, you can actually glue your sheaves. So he says then there exists unique sheaf F, which restricted to UI is just this Fi. And if we call these restriction maps psi I, if you first apply psi I and then phi ij, then you get psi j. And when he says unique, he really means unique up to isomorphism. So it's not literally unique in that sense. So this is just telling you that you can think of sheaves also as local objects on some open cover, satisfying gluing conditions. So later we will have some very concrete X with some very simple pieces UI, and on them we understand the sheaves very well, and then we want to glue them to a global object. So that's what we'll do later. Let me also recall the notion of a vector bundle, but now in the algebraic setting. So a vector bundle of rank R on a variety X, it's a morphism from some variety E to X with the following properties. So vector bundle means, so intuitively above all points of X, you want to put an R-dimensional vector space, which is E restricted to X, and it's just a fiber over the point X. So what you're doing here is you have a morphism from E to X, and above on each fiber you put the structure of a vector space. But you want a little bit more. You don't want that all the fibers are just vector spaces. You want that this behaves nicely if you vary X in a continuous way or an algebraic way. So you want an open cover of the base, UI. And what you want is that over UI, your vector bundle trivializes. So when I write here E restricted to UI, I mean the inverse image of the open subset UI. And what you want is on here that E is nothing but the product, the trivial vector bundle, UI times CR. And in fact, you want even more, you want that the map down to the base is just projection to the second vector. So, so this is what you want. And you want a little more. You want that if you start on some fiber X, where X lies in two charts, UI and UJ, if you first go via psi I to UI and then via psi j inverse, you go back to the fiber, then you want this not to be just any map, but you want it to preserve the vector space structure. So this is what's called a vector bundle. You may have seen this over differentiable manifolds and over the real numbers, where all maps are smooth, but this is the algebraic version. And then as an exercise, you can think about what do I mean by a morphism, a map between vector bundles. So are there any questions at this stage? If not, let's move on. So in this talk, we'll talk a lot about torus actions. So for an algebraic geometer, a torus is actually a number of copies of C star. So C star times C star times C star. So this is naturally a group. And this is what algebraic geometers call the algebraic torus. And let's assume that the algebraic torus acts on some variety X. So we'll be talking a lot in this in these hours about varieties with the torus action. So let's first define what we mean by a T equivariant structure on a vector bundle. So what we mean by this is just an action of the torus on the vector bundle, on E, which is compatible with the action down on the variety. So you can write that as this diagram. Down on X we have a torus action, T times X to X. And a T equivariant structure means you have a torus action on E, the total space of the vector bundle. such that this diagram commutes. But you want, again, a little bit more. If this diagram commutes, it means that the fiber over X maps to the fiber over T times X. So you get some map from the fiber over X to the fiber over T times X. And you don't want this to be just any map, but you want it to be C-linear. So you should preserve all the structure you have. These fibers are vector spaces, so you want to preserve this structure. So actually, it's interesting that you can also define a notion of T-action or T-equivariant structure on sheaves. The definition is a little tricky to write down. It takes quite some notation. So they will come back later. I won't define them here, but we only need them. We only need a few facts about them. So I'd rather state later on what we use about T-equivariant structures on sheaves than give you the full definition. So I'm not going to do that, but for now, I just say there exists a notion of T-equivariant structure on sheaves as well. But later this will become very concrete. And an exercise is define T-equivariant morphisms between T-equivariant vector bundles. Okay, so now I want to be able to go between vector bundles and sheaves. So there's a correspondence between these objects. So I hear some noise coming from my window. Is it bothering you or not? I can close my window.
No, I cannot hear anything.
Okay. So, is there a question in the chat? It's okay. Okay, good. Yeah, if something is not audible, please let me know. So now let's say we have a sheaf of modules. Then let's first define what I mean by a locally free sheaf. So a locally free sheaf is a sheaf with the following property. There is some open cover ui of x, such that if you restrict to ui, you just have R copies, let's say rank R locally free sheaf, you have just R copies of the structure sheaf. So R copies of the trivial sheaf. And now I claim that essentially vector bundles and locally free sheaves are the same. So how does this work? Well, let's first go from a vector bundle to a locally free sheaf. So suppose we have a vector bundle, P from E to X, and then you can define what you mean by sections on an open subset U. So what do we mean by sections over U? That just maps that go from U into the variety E, the total space of the vector bundle, restricted to U, so over U. And you want that if you go around, that you get the identity. So if you first map into the vector bundle and then you project, you should get the identity. So in particular, these sections are always injective maps. So this we define as SE over XU. So these are the sections of the vector bundle over U. Now, these objects here, they actually form a sheaf. So you can show that this is a sheaf of sets. It's in fact a sheaf of abelian groups and even a sheaf of modules. And the exercises prove that this is actually a rank R locally free sheaf on X. And the idea is that locally the vector bundle trivializes, and that will also induce a trivialization of your sheaf as I just defined it. So in fact, it turns out you lose no information when you do this. So you have two categories. We have a category of vector bundles with maps between them. We have a category of coherent sheaves, and in there the locally free sheaves. So the locally free sheaves of finite rank. And this map, which assigns to E the sheaf of sections, is actually an equivalence of categories. So really they are the same objects. And often algebraic geometers, sometimes they don't even say, sometimes they say let E be a vector bundle and they immediately think about the corresponding sheaf. So we jump between these all the time. Specifically, we also jump between line bundles and rank 1 locally free sheaves, which are called invertible sheaves. So this is also actually an exercise in Hartshorne. It's a bit of work to show that this is an equivalence of categories. I mean, here I recommend you look at it for X variety. In this exercise, it's more difficult because he does it over an arbitrary scheme. It becomes a little simpler if you try to prove this just over varieties. Yeah, so now we do need schemes a little bit. but we will focus on affine schemes. So let X be an affine scheme. So that means it's the spectrum of a ring. It's a ring of global functions, OXX, which I will assume to be Noetherian. In fact, for this entire slide, it's fine if you take X a variety, but it has to be thought of an affine variety, but thought of as a scheme. So it means the spectrum of its ring of functions. And then there's one very special property. What's very nice about coherent sheaves is that on affine schemes, you lose no information if you take the global sections of your sheaf. So if you have a coherent sheaf on X and you take the global sections, you get some module over the coordinate ring, finitely generated module, and this is an equivalence. So this is somewhere at the start of Hartson chapter 2. This is the key fact about why we care so much about coherent sheaves. If you take global sections and you're on an affine scheme, you lose no information. But this is very specific to affine schemes. So now in some sense, the only example we need locally is of affine n space, which is just the spectrum of its ring of functions, namely the polynomial ring in n variables. So you can define an action on this affine space by the torus C star to the n. And we just use the standard torus action. So the way we act on coordinate function xi is by multiplying with ti. So literally t1 up to tn times xi is ti xi. So we take this simple action. It gives you an action of this algebra, on this algebra. And in fact, this action gives a decomposition of your algebra. It gives a Zn grading, essentially in all monomial ideals. So you can write a Zn grading on this algebra by monomial ideals, by one-dimensional spaces. And what we'll use now is we think of the elements of Zn as characters. So there's a correspondence between elements in Zn and characters. So if you have an n-tuple of integers, m1 up to mn, you can associate a character to it, a function chi-m from the torus to C star. And it's just, on a point t, it's just t1 to the m1 times t2 to the m2, etc. So characters here are just group homomorphisms from t to C star. So there's an equivalence between n-tuples of integers and characters of this torus. And the reason I'm saying all this is because this example above actually generalizes. If F is a T-equivariant coherent sheaf on X, I didn't define for you what a T-equivariant structure is on a coherent sheaf, but the only fact we need is that if you have this, such a structure, it gives you a T action on the global sections. And you can in fact decompose the global sections into weight spaces, into spaces with respect to this character group Zn. And in terms of this decomposition, the action becomes very concrete. If I take a vector v in the weight m space in this eigendecomposition, the action on the vector is just evaluating the corresponding character in t, gives you some complex number, and you multiply it by this element in the module. So this is just saying that if you have a coherent sheaf with a T-equivariant structure, at the level of global sections, it gives a T action, and this T action is completely determined by the decomposition into eigenspaces. And it turns out that if you look at sheaves, coherent sheaves with a T-equivariant structure, well, now this equivalence at the top of the page, it just becomes an equivalence between finitely generated modules over the polynomial ring, but with a Zn grading. So looking at T-equivariant coherent sheaves on this affine space, so here X is really, maybe I should have written here Cn. X is really Cn here, so T-equivariant coherent sheaves on Cn, they are just the same as Cx1 up to xn modules with a Zn grading. Okay, so this is a very algebraic slide. Are there any questions? So here I'm really just stating this as a fact. This is not something that I here prove right now. So this, you can just think of this as the definition of equivariant structures here. And then there's one topological slide before we start talking about the proper topic. So if you have a compact complex manifold, there's an underlying real manifold, and that real manifold has Betti numbers. So what is the ith Betti number? It's the rank of the ith singular homology group, or by Poincare duality, ith singular cohomology group. And the alternating sum of these Betti numbers is the topological Euler characteristic. So what's interesting is you can actually also define topological Euler characteristics for schemes over the, let's say, over the complex numbers. So we don't need to know the definition, we only need to know the rules, a bunch of calculation rules for working with these Euler characteristics on schemes. So first of all, this Euler characteristic doesn't see the scheme structure. So it's always the Euler characteristic of the scheme. It's just the Euler characteristic of the underlying reduced scheme, and even of the C-valued points of that reduced scheme. So if you have a separated finite type scheme over C, it has an underlying variety, and you really, doesn't matter whether you take the Euler characteristic of the scheme or the underlying variety. So it doesn't really see the scheme structure. And also it behaves well on products. The Euler characteristic of the product is the product of the Euler characteristics. And also, if you happen to have a smooth projective variety, you can switch to its complex analytic topology. And then in terms of the complex analytic topology, this new notion of Euler characteristic, it is just the old one. And then finally, the most importantly perhaps, is it behaves very well under cutting and pasting. If you have a closed subset, or even a locally closed subset in a scheme, the Euler characteristic of X take away Z is the difference of the Euler characteristics. And perhaps most crucially for us today is if you have a scheme of variety with a T action, if you want to calculate the Euler characteristic, you only need to know the Euler characteristic of the fixed point scheme. So we don't need to know how you define the fixed point scheme as a scheme. What's important is its C-valued points, its closed points, are precisely what you expect, namely those points that are left invariant under the T action. So for naive varieties, this is just really the fixed locus, as you would think of fixed locus. So with this set of rules, you can already calculate the Euler characteristic of many objects. For instance, if you assume that the Euler characteristic of a point or affine space is 1, you can already start calculating the Euler characteristic of the torus, which is 0 in fact, and the Euler characteristic of Pn. And if you do the calculation, you'll find that this is equal to n plus 1. Okay, so these are some preparations. Are there some questions? Please ask. Any question is a good question. If not, let's start talking about torsion-free sheaves. So what is the goal of this lecture? So we have a smooth projective variety. And what we want to do is we want to study all vector bundles on there at once. Maybe modulo isomorphism. Or, as we have just seen, it's the same as studying all locally free sheaves at once, modulo isomorphism. So this is, as such, it's just a set. But ideally, we would like this to be, our dream would be that the set of all vector bundles, modulo isomorphism, is itself a compact complex manifold. Because if we have this, we can really start doing integrals over these moduli spaces. Which is actually something that turns out to be relevant to physics. But, okay, this is what we want. But I'll argue that for this to be a compact space, locally free sheaves is not enough. So this is too restrictive. So we'll be talking about torsion-free sheaves. So a coherent sheaf on a variety X, for it we define a support and a dimension. The support is the set of points where the stalk of your sheaf is non-zero. So this is some closed subset of your variety. And you say that the dimension of your sheaf, you define it to be the dimension of this support, of this closed subset. And so it can be that the support of your sheaf is just everywhere on X, but it could also lie on some curve or some surface. So what is then a torsion-free sheaf? Well, a torsion-free sheaf is a sheaf with the property that all its non-zero subsheaves, E in F, have maximal dimension, have dimension equal to X. So yeah, F is called torsion-free if the dimension of E is the dimension of X for all E inside of F, except the zero sheaf. So already you can do some nice exercises with this definition. For instance, you could try to prove that a locally free sheaf is always torsion-free. But on this slide, I'm assuming that X is a variety, and a more challenging exercise, so there's a star here, means that the exercise is a bit harder, is you can also ask the question, is it still true that the locally free sheaf is torsion-free if your scheme X is no longer a variety? But anyway, that's not something we need today. So now we want to zoom in on torsion-free sheaves on C2. And we also assume that our torsion-free sheaf has a T-equivariant structure, so a torus action. So then the following data is equivalent. A T-equivariant coherent sheaf F on C2, and the following linear algebra data. So we have already seen, so now all I'm going to do is I'm going to repackage the equivalence that I mentioned here earlier at the bottom of this page. So F decomposes, its global sections decompose into weight spaces. So each of these Fxm's here is a finite dimensional complex vector space. So the fact that your sheaf F is coherent forces this weight space to be a finite dimensional complex vector space. So you get, so each of the weight spaces, let's now call it just Fm, straight Fm, is a finite dimensional complex vector space. And this is a module, so there's a multiplication by x1, or a multiplication by x and a multiplication by y. So if you multiply a vector in Fm with x, you land into Fm plus 1, 0. You move one weight space to the right. Whereas if you multiply with y, you move one weight space up, because we're in the category of set 2 graded CXY modules. And of course, x times y is y times x, because we are in a polynomial ring. So you want that all the squares commute here. And finally, you want the corresponding module, so x1 is x here, x2 is y, you want it to be finitely generated. So you should really think of this as a picture. So you have the lattice set 2. On each lattice point, you put a finite dimensional complex vector space. Then between each neighboring lattice points, you put a C-linear map, and you want that all squares in your grid commute. And you want a coherence condition. You want that if you put this all together into a big module, that it's finitely generated. So in this sense, a T-equivariant coherent sheaf is just a bunch of linear algebra data. It's a complex vector space on each lattice point with maps between these, with some finiteness conditions. So in this language, being torsion-free becomes a very concrete notion. So it turns out, in terms of this linear algebra data, your coherent sheaf is torsion-free precisely if all these maps between neighboring lattice points are injective. And in fact, you can even take them to be inclusions. So yeah, torsion-free sheaves are then just like a big double-graded grid of vector spaces on Z2. So it becomes a very clear bunch of linear algebra data. So yeah, one exercise is to prove the inclusion from left to right. The one from right to left is harder. And also we can, since we want our sheaf to be coherent, we have a bunch of facts here. Namely, we don't want infinitely many generators, which means that if we go very much to the left in our lattice, these weight spaces become 0. Or if we go very much down, they also become 0. And on the other hand, if we move very high up in the first quadrant, so M1 and M2 are sufficiently large, well, we're not allowed, it must remain finitely generated, so we're not allowed to put, to keep putting elements, generators, homogeneous generators into our module. So at some point it needs to stabilize to a vector space of some fixed dimension. And that dimension is precisely the rank of your sheaf. And in fact, it's even true that if you look in this grid and you go very much to the right, it also has to stabilize to a flag of this complex vector space. Whereas if you move very much up, you also stabilize to a flag of this vector space. So this is what coherent sheaves on C2 with a T action look like. It's just a double filtration of complex vector spaces that stabilizes to CR at some point. So somewhere in the grid, you're equal to CR. So I'll actually make this more concrete for some low ranks in a minute. So now let's talk about T equivariant vector bundles on the complex plane, C2. So suppose you have just two flags, GM and HM. So let's say if you go very much to the left in the flag, you get 0. And if you go sufficiently to the right in the flag, you stabilize to CR. Then, well, according to the previous slide, you can build a torsion-free sheaf, F. So you define FM1, M2 to be the intersection of GM1 and HM2. So they both lie in CR, so we can just intersect these spaces. And as maps between these, so on each lattice point, M1, M2, we put GM1 intersected HM2. And then by construction, since these are flags, we can always go from one lattice point to the neighboring lattice point on the right or up by inclusion. So we take as our maps the inclusion maps. So we put a big, on the grid, we just have a big bunch of inclusions of vector spaces. So that in particular defines you a rank R T equivariant torsion-free sheaf, simply because all the maps are inclusions. And it turns out that the torsion-free sheaves that you obtain in this way are precisely the locally free sheaves. So the T equivariant rank R locally free sheaves are precisely the ones that are obtained from this construction. Just take two flags and intersect them. And the proof, very roughly, this is not really a proof, but the point is that for locally free sheaves, they're actually determined by restricting them to C times C star and C star times C. And then already you can really start playing nice games. So for instance, you can prove that a rank 2 T equivariant locally free sheaf on C2 is always the sum of two rank 1 T equivariant locally free sheaves. So, and then a slightly more challenging question is, what about rank R T equivariant locally free sheaves on C2? In fact, it turns out that these also always split into T equivariant rank 1 locally free sheaves. There is actually a non-equivariant version of this. On affine spaces, vector bundles are always direct sums of line bundles, but in the non-equivariant setting, this is actually a very hard problem. But here it becomes purely a linear algebra problem. Are there any questions? If not, let's move on. So let's talk about reflexive hulls. So if I have a torsion-free sheaf on a smooth variety, there is a natural map from F to hom of hom F, 00. So you dualize twice here. And it turns out that if your sheaf is torsion-free, this map here is an injection. And this map, this sheaf F star star is called the reflexive hull of F. Okay, and again, it's a nice exercise to describe what this map between these sheaves here is. And it turns out that if your variety X has dimension 2 or less, this double dual is always locally free. So you can embed a torsion-free sheaf always into its double dual. But again, the story is that if you're on C2 and if you're in the T equivariant setting, these type of maps become very concrete. So suppose we have a rank R. This should say if we have a rank R T equivariant torsion-free sheaf. Sorry, that's a typo. So if we have a torsion-free sheaf here, so this corresponds to, again, on the lattice set 2, we put finite dimensional vector spaces and inclusions if you go up in the grid. So in this case, you can describe the reflexive hull very clearly. I mentioned that if you go very much to the right in the grid, you get a flag of CR. If you go very much up in the grid, you get a flag of CR. So, as we just saw, if we have two flags, we can construct a locally free sheaf, just the intersection of the two flags. So this double dual, it just becomes the vector bundle corresponding to these two flags. And in particular, by construction, this F M1, M2 will lie in the intersection of these two flags. So this double dual map is nothing but this inclusion here at every lattice point. So this double dual construction becomes very concrete in this torsion-free case on C2. Let's make it a bit more simple. Let's only look at T equivariant rank 1 torsion-free sheaf, locally free sheaves, so line bundles. Then the following data is equivalent. Well, in this case, the limiting vector space at infinity should just be C. So you can only have inclusions of C into C or 0 into C at the vector space level. So a torsion-free sheaf of rank 1 on C2, T equivariant, it's just putting C or 0 on the lattice point and inclusions between them. But if you're moreover locally free sheaves, you have to come from this intersection property. So you just have a flag jumping from 0 to C. You have two of them. So if you intersect, all that happens is you just have some quadrants on which you put C and outside of which you put 0. So a T equivariant line bundle is nothing but an element of set 2. So you just specify the unique location, the location where the unique homogeneous generator resides. So this very combinatorial linear algebra description of equivariant vector bundles, this on this page here, if you specialize it to rank 1, the only data you have is just a lattice point, A1, A2. For instance, the structure sheaf corresponds to 0, 0. Then it's a nice exercise to look at what ideal sheaves look like in this language. So the ideal sheaf of y equals 0 or x times y equals 0. They have nice descriptions in terms of this, this linear algebra data. So let's go one rank up. So here it becomes a little more rich. So let's look at T equivariant rank 2 vector bundles on C2. So what does this look like? Well, this time we have two flags. Let's say one flag that's specified by an integer AI, a non-negative integer delta I, and a one-dimensional subspace VI of C2. So the rank here is 2, so we need to specify a flag in C2. So what is AI? So the flag starts with 0, then at some point it jumps to VI, let's say at position AI, and then a little further, at AI plus delta I, it jumps to C2, and then nothing changes. So this is just one flag. It's 0, at some point VI, at some point C2. However, we do, when I write this notation here, I do allow delta I to be 0. If I write delta I to be 0, it means you jump straight from 0 to C2. So there's no intermediate space. So a rank 2 T-equivariant vector bundle, it's nothing but an integer A1, A2, non-negative integer delta 1, delta 2. And if delta I is positive, a one-dimensional subspace Vi in C2. So this is all there is to a rank 2 T-equivariant vector bundle on C2. Now suppose you have such an object, F, corresponding to 2 of these flags. And let's assume that delta 1 and delta 2 are positive, and that V1 and V2 are different. And now let's look at the following limit. Let's look at the limit where vector space V1 becomes equal to vector space V2. But we want to keep the dimensions of these eigenspaces Fm, we want to keep them equal. So in that case, you will find that the limiting object is actually no longer a locally free sheaf. So if we have these vector bundles here, F with V1, V2 not equal, if you take the limit where V1 goes to V2, keeping the weight spaces fixed, the limiting object is a torsion-free sheaf of rank 2, T-equivariant, but it's no longer locally free. And what this suggests is that if we want to build a moduli space of vector bundles of locally free sheaves, we should allow torsion-free sheaves, because in the limit of a family of locally free sheaves, you can actually encounter a torsion-free sheaf. And if we want a compact moduli space, well, we want that limits also lie in moduli space. So we want to add torsion-free, this is motivation for adding torsion-free sheaves to your moduli space. So now so far I've only been talking about T-equivariant torsion-free sheaves and T-equivariant locally free sheaves on C2, but now we want to go global. So let's talk about T-equivariant torsion-free sheaves on P2. So what I'm now going to describe is due to Kliashko. So we're on the projective plane with coordinates x0, x1, and x2. And on the projective plane, we have 3 charts where x alpha is non-zero, and each of these charts is just a copy of C2. And we have a torus action on P2, namely t times x0, x1, x2 is x0, t1, x1, t2, x2. So we have an action of the torus on the projective plane. Now, okay, let's say we have a rank R T-equivariant torsion-free sheaf on P2. Okay, we can, since these charts here are invariant under the torus action, we can restrict the torsion-free sheaf to each of the charts, and then we have a T-equivariant torsion-free sheaf on C2, just by the previous slides. So whenever you have a rank R T-equivariant torsion-free sheaf on P2, you get 3 rank R T-equivariant torsion-free sheaves on C2. And we know that each of those corresponds to some big double filtration on a lattice. So you get 3 families of double filtrations on the lattice corresponding to each of the 3 charts. But now we want to go back. Now we want to say, suppose we have on each of the 3 charts U alpha, we have the data of a rank R T-equivariant torsion-free sheaf. In other words, let's say we have 3 of these double filtrations, 1 for each chart. Can we glue it back globally to a T-equivariant torsion-free sheaf? So can we glue these local sheaves to a global torsion-free sheaf? And this is where the very first slide comes in. So by a T-equivariant analog of the Hartshorne exercise on gluing, you can work out what it means for these torsion-free sheaves to glue. So you write these Hartshorne conditions in terms of the linear algebra data that we had before. And then you'll find that these local torsion-free sheaves, they glue to a global one on P2 if the following gluing conditions are satisfied. So this upper bracket alpha determines which of the three charts we're in. So you want that if you, let's say we start in chart U0, we have some double filtration. We move very much to the right, which is this F infinity M. And we want that this precisely matches the Fm infinity of the next chart. So on the next chart, we also have a possibly different double filtration. And there, if we very much move up, we get some flag, and we want those two flags to match. And now we go around P2. So we also want that if we move very much to the right in the second chart, we get the limit if we very much move up in the third chart. And then if we very much move to the right in the third chart, we get the filtration obtained by moving very much up in the first chart. So this is precisely the gluing data in terms of the linear algebra data. So if we have 3 filtrations of CR for each of the charts, then they glue to a global sheaf precisely if these gluing conditions are satisfied. So now we go back to just line bundles. Well, in the case of a line bundle, I told you we just have a double filtration of C. And in fact, we only have to specify the location of the generator. So a T-equivariant line bundle on P2, well, a priori, we just have a line bundle in each of the 3 charts. So we have 2 plus 2 plus 2, we have 6 integers. But then we need to specify these gluing conditions. Well, in this case, the gluing conditions just mean when you jump from 0 to C. So we get these 3 equations. So we get 6 variables and 3 linear equations. So in other words, if we know A10, A20, and A21, let's call them ABC, we have completely determined our T-equivariant line bundle. So T-equivariant line bundles are nothing but triples of integers. That's all. And this is what's called the T-equivariant Picard group of P2. So we just calculated that this is set to the T-equivariant line bundles on P2. And then the T-equivariant rank 2 vector bundles. So now it becomes a little more interesting. So for each chart U alpha, we have a filtration, we have 2 flags of C2. And these flags are determined by saying when it jumps from 0 to VI alpha, a one-dimensional subspace of C2. And then when it jumps from VI alpha to C2, this will be at AI alpha plus delta I alpha. And again, it's allowed that you jump straight from 0 to C2, in which case delta I alpha 0. So we now have 6 flags jumping from 0 to possibly a one-dimensional space to C2, and we tell when the jumps take place. Then if you unravel these gluing conditions, it just means that the A2 alpha is A1 alpha plus 1, and the delta 2 alpha is the delta 1 alpha plus 1, and the V2 alpha is the V1 alpha plus 1 for alpha modulo 3. So it's far less data than we had above. In fact, what this shows is that really to specify a T-equivariant rank 2 vector bundle on P2, we just have to specify 3 integers. The remaining 3 of these AI alphas are then determined by the gluing conditions. We have to specify 3 flags. So 3 deltas, delta 1, which we define to be delta 1, 0, delta 2, delta 2, 0, and delta 3, delta 2, 1. And 3 one-dimensional subspaces of P1. So we take V1, 0, V2, 0, and V2, 1. And remember, if delta I alpha is 0, we actually omit VI alpha. So it's allowed to jump straight to C2. So if we take all the deltas positive, really we have 3 points on P1. So here I'm thinking of a one-dimensional subspace of C2 as a point on P1. So this identification I made implicitly here. So yeah, so the data of a T-equivariant rank 2 vector bundle on P2, it's just an element of set 3 times set bigger than or equal to 0, 3 times P1 cubed. But again, if delta I is 0, we don't specify a point on the corresponding P1. So are there any questions? Let me also look at the time. So any questions so far? Please ask. I can go back. Maybe also we should take some break at some point.
Yeah, I forgot to mention, but whatever you want to take a break, it's like 5 or 10 minutes is fine. You just let me know. It's better.
Right, right. So maybe first, are there any questions or comments, or should I repeat something? So maybe I should have had some pictures in here, but really this is stuff you can draw. So you really have, if you have a rank 2 torsion-free sheaf on P2, you really, on each of the 3 charts, you just look at the lattice Z2, this grid, and you really put a double filtration of vector spaces on the lattice point that's stabilized to CR, where R is the rank. And then these double filtrations have to stabilize if you go sufficiently far to infinity, and they have to satisfy these gluing conditions. I mean, I do have a board behind me, so if you'd like me to draw something, please ask, and I can actually do so.
Maybe you can mention your goal for this talk, because
yes, so the goal will be to calculate, so first of all, to build the moduli space. So we are going to build the moduli space of all sheaves. And what we want is we want to calculate the Euler number, the Euler characteristic of the moduli space. And then if the variety has a torus action, by the rule that I wrote here, we only need to calculate the Euler characteristic of the fixed point locus. And it will turn out that the sheaves in the fixed point locus are these T-equivariant sheaves, roughly speaking. And they are given by very concrete data. So those Euler characteristics we can really calculate. And it turns out that these Euler characteristics of moduli spaces of sheaves and vector bundles, they are precisely what's important in topological quantum field theories. But yeah, this I'll mention later in the talk. So the goal is really A, to describe what is the moduli space of sheaves, and B, to calculate the Euler characteristic by calculating the Euler characteristic of the fixed point locus. That will be the goal. Yeah, so maybe now, if there's no more question right now, we should perhaps take a short break. Okay, so let's continue. And again, if you want me to draw some picture in low rank of what these things look like, I can do this. But now let's go to a little bit of topology, namely Chern classes. So this now for a moment, we were really talking about sheaves with a torus action, torsion-free sheaves with a torus action on C2 and P2. And we really reduce this to linear algebra data. Now, for the moment, we go back to just an arbitrary smooth projective variety X and a coherent sheaf on there. So we do want to fix some topology of our sheaves before we continue. So we already argued that in our moduli space, we want to have torsion-free sheaves, but it's a bit much now. So we want to fix some topology. So we so I'll give a very brief overview of Hartshorne Appendix A. So we want to fix some topology of our sheaves. So this is called the Chern class, the total Chern class. And it's something that lives in H2 star of X sets, the even singular homology of your variety. Actually, in Hartshorne, it will lie in the Chow group, but we do the version where it lies in homology, cohomology. And yeah, so this is Chern classes. Okay, there are a few details. Singular cohomology may have torsion, so we mod out by torsion. And also the top cohomology group, this is very important. The top cohomology group is isomorphic to Z. So the top Chern class can be seen as an integer. And one way to obtain this isomorphism is to use the canonical orientation induced by the complex structure, or if you have seen Poincare duality, the generator of this set is the Poincare dual of the point class. But this is just some fine print. So there's a equivalent notion called Chern character, where you start with the rank of your sheaf and then the first chunk character, second chunk character. Well, in this talk, we only go up to 2 actually. So we only need to know how to express this data in terms of each other. The first chunk character is just the first chunk class. And the second chunk character is half C1 squared minus C2. So what's important here is you can actually, so when I write squared here, I'm using the cup product in cohomology. So I can multiply cohomology classes. C1 is a class in H2. If I multiply it with itself, I get a class in H4. If I then am on the surface, which I'll later be, I actually obtain an integer. There is some calculus of these churn classes. So if you have a short exact sequence, the total churn class of the middle is the product of the 2 churn classes, and whereas churn character is actually additive. So these things behave well in short exact sequences. And then for locally free sheaf, well, you have that as soon as the degree of your churn class is bigger than the rank, it's 0. And of course, there is no cohomology above the dimension, so there's also no churn classes above the dimension of your variety. And then there is a nice formula for line bundles. So for a rank 1 sheaf, the churn character is just e to the power C1 of L. So you only need to know the first churn class. And now what we want to do is we want to make our moduli space a little bit smaller. So we argued that instead of looking at the space of all vector bundles, we want to look at the space of all torsion-free sheaves, modulo isomorphism, because we already saw that a limit of a family of locally free sheaves can become torsion-free. But we do want to make the space a bit smaller by fixing the churn character of our sheaf to be some fixed vector in cohomology. So this you should think of as fixing the topology of your sheaves. I see there's a small typo here. The E should be an F. So when I write MXV, I look at all torsion-free sheaves F on X with a fixed churn character V in cohomology. So let's look a little bit at churn characters of vector bundles on P2. So in this case, the cohomology groups are very easy. So as an algebra, this is just a polynomial ring in H modulo the relation H cubed is equal to 0. So here H, little h, is the Poincare dual class of a line, and little h squared is the Poincare dual class of a point. So again, the product on this cohomology here is the cup product. So then, okay, we already saw in the previous part that a T-equivariant line bundle is specified by 3 integers if we're on P2. So previously, if we restrict to each of the chart, we got 2 integers, in fact, telling you where the generator lies. But due to the gluing conditions, they're actually not 6 integers, but 3 integers. And in terms of those 3 integers, the first churn class is actually a very concrete thing. It's minus the sum of those integers times the class of a line. So this is what the first churn class is. So from this, we also see a line bundle is trivial non-equivariantly. So if you forget the equivariant structure, L is trivial precisely if its first churn class is trivial. And this happens precisely if the sum of those 3 integers is 0. So we can detect when an equivariant line bundle is trivial, but possibly with non-trivial equivariant structure. In fact, there is a short exact sequence. If you look at the Picard group of T equivariant line bundles, that's a copy of Z3. You can take the first churn class. You get, well, something isomorphic to the Picard group on P2. And the kernel is just a copy of the character letters. But yeah, maybe this is not so important. But now what's interesting is let's go to a rank 2 locally free sheaf F. So in this case, this was specified by a priori for each of the 3 toric charts, you have 2 flags. But then due to the gluing conditions, only 3 flags are left in the end. And those are described by ABC, delta 1, delta 2, delta 3, V1, V2, V3. And then purely in terms of this linear algebra data, I can tell you what the churn character of F is. It's given by this rather large formula. So the rank is 2. Then it's this number times the class of a line. So -2, a plus b plus c, plus delta 1 plus delta 2 plus delta 3. And then plus something very explicit, half a plus b plus c squared times h squared, similar term. And then you see somewhere where the linear algebra comes in a bit, minus delta 1, delta 2 times 1 minus the dimension of the intersection of the two subspaces v1 and v2 times h squared, same for 2 and 3, the same for 3 and 1. So this formula looks very complicated, but my claim is already with the tools that we have set up so far, you can actually prove this formula. But you do need some facts. So it turns out one fact is that the Chern character only depends on the dimensions of the weight spaces that we put on all the lattice points. It does not depend on the maps between these weight spaces, on the inclusions. So it doesn't see the module structure. That's one fact. And another fact is, if you have a T-equivariant structure, a T-equivariant short exact sequence, EFG, and if this last sheaf is zero-dimensional, or actually I could have just phrased this for, okay, if G is a zero-dimensional T-equivariant sheaf, that means in each of the charts there are only finitely many weight spaces which are non-zero. So actually such sheaves are never torsion free, but they are, according to the beginning of the lecture, T-equivariant coherent. Then the Chern character is something very simple. It's just the total sum of the dimensions of the weight spaces times h squared. So with these facts, you can already prove this formula. It's a bit of a challenge, but you can build another sheaf that has the same weight spaces as F. And then that particular sheaf you can build up out of copies of line bundles where you possibly remove zero-dimensional sheaves. So my claim is, yeah, if you know these two facts, you can already prove this formula. But it's better if you want to actually do this, I encourage you to do some very concrete examples where you really choose delta 1, delta 2, delta 3, v1, v2, v3, and really try to build up your sheaf from simpler pieces. So then with the calculus of this section, you can really calculate this Chern character. And then, okay, you could, if you really, once you start feeling comfortable on P2, you can repeat everything that I said on other surfaces like P1 cos P1. Okay, so unfortunately, we're still not done with our moduli space. So we now have MXV, sheaves on X with Chern character V, torsion-free sheaves. But it's still too big, this moduli space. So we need to impose what's known as stability. So actually this part will be general. Let's first start with a smooth projective variety of dimension D, and we put a very ample divisor H on it. So you should think of this as X being embedded in a projective space, and this is the restriction of the line bundle O of 1. So then for a torsion-free sheaf, F on X, we can define its slope. So its slope is its first Chern class times this ample divisor H to the power D minus 1. So this is a number, it lives in the top cohomology. So it's a number, and we can divide it by the rank. So this is called the slope of the sheaf. And then a sheaf is called stable if for all subsheaves E with rank positive and rank smaller than F, the slope of E is smaller than the slope of F. So because of this rank condition, for rank 1 sheaves, stability is automatic. You don't have to check anything. It's an empty condition. And another interesting fact is if you have two stable sheaves, E and F, and the slope of E is bigger than the slope of F, then there are no morphisms from the sheaf E to the sheaf F. So this is actually a statement you can try to prove from the definition. So yeah, so actually at the very end of these lectures, I have a list of references. The first reference is Hartshorne, but then all the facts that I state in this lecture can actually be found in great detail, in full detail, in one of the references at the end. And another interesting fact is that a stable sheaf is simple. So it means that all endomorphisms are just multiplication by a complex scalar. This is a little harder to prove. So it follows by showing first that a non-zero sheaf, non-zero endomorphism is an isomorphism, and then using that finite dimensional division algebras over C are trivial. But anyway, this is not so important. We can also take this as a fact. And another interesting fact is, well, a torsion-free sheaf we can always embed in its double dual. And actually, F is stable if and only if its double dual is stable. And this you can prove if you know that the quotient of the embedding is a sheaf of codimension 2 or more. So now we're going to look at, so the whole point of this lecture, for instance, is like, say you want to learn moduli of sheaves. You have this book by Huybrechts and Lane, and you'll find it's quite complicated. But the point is that all these notions, Chern characters, stability, they become very concrete if you're in the setting where you have a variety with a torus action and your sheaf has an equivariant structure. In those cases, all of those complicated notions can be reduced purely to linear algebra statements. So let's do this now for stability. So as a very ample divisor, we just take the class of a line. And now we fix a rank 2 T equivariant vector bundle. So actually here this is a typo, I should not put mu stable here. So we start with an arbitrary rank 2 T equivariant vector bundle on the projective plane. So that means we have 3 flags specified by integers ABC, delta 1, delta 2, delta 3, and one-dimensional subspaces V1, V2, V3. So first of all, if one of the delta i's is 0, so that means in the corresponding chart, so in the flag, there's a jump from 0 to C2. The first claim is from the historic picture. You can already see from this linear algebra picture, you can see that your F is a sum of 2 line bundles. But then if that's the case, the endomorphism group can never be C. It will be C2. So such a sheaf cannot automatically not be stable. And similarly, even if all the deltas are positive, so all the flags really go from 0 to 1 to 2, so they're full, it can still happen that 2 one-dimensional spaces coincide. So if some of these VI's are not mutually distinct, they coincide, then also you can show that, as an exercise, you show that your rank 2 vector bundle is a sum of 2 line bundles. So it's not simple, so it's not stable. So the only possible stable rank 2 vector bundles, T equivariant, they have all the delta i's positive and they have all the VI's mutually distinct. So you should imagine a projective line with 3 distinct points on it. Okay, so these are the potential stable sheaves. So now if you have one of these VI's, they will determine a maximal T equivariant line bundle, Li, on F. So in each chart, you take VI and you extend it as far as possible, and that will define you a T equivariant line bundle. And now you use this Chern character formula of the previous section to calculate the slope. So with the formulae that I've given you, you really can calculate this slope for the rank 2 sheaf and for these line bundles Li. So then if the sheaf is stable, well, the slope of mu, let's say mu L1, has to be smaller than the slope of mu F. So this becomes just an inequality on these numbers, delta I. It just forces delta 1 to be smaller than delta 2 plus delta 3. So F being stable forces delta 1 to be smaller than delta 2 plus delta 3, and then similarly for the other deltas. So it turns out, so now I've only sketched how you show that if the sheaf is stable, you get these three inequalities on your deltas. But it's in fact an if and only if. And the reason that's the case is you can prove that to test stability, you only need to look at equivariant subsheaves. And then, okay, you can try this on P1 cross P1. So now we can finally come to our moduli space. So this was just a P2 for a moment. Now we go back to the general setting, arbitrary X, arbitrary churn character, arbitrary rank. And I put one more condition. I want the greatest common divisor of the rank and C1 times H to the power D minus 1. I want it to be 1. And then it turns out that there does exist a nice compact moduli space of sheaves. However, it is a scheme, it's not a variety, and also it's not smooth, unfortunately, but there exists a projective scheme with the following properties. The points in your scheme, the closed points, are precisely the isomorphism classes of mu-stable torsion-free sheaves with a fixed churn character. So now we have achieved our dream, we have a nice projective scheme. But we fixed the topology, we fixed the churn character. And we did have to insist on torsion-free sheaves being there. But we did have to impose this stability condition. And it's not just that this scheme parameterizes all, so the points of the scheme are not just isomorphism classes we're interested in, they also behave well in a family. So this second bullet is a bit technical, so you can ignore it. But if you happen to have read a bit further in Hartshorne, you can say the following. If you have a family of sheaves, so you have some base scheme S, and you have a family of sheaves F, so over each point in S, you have a sheaf Fs. And let's say all of these Fs's are mu-stable sheaves with the right churn character. Well, then you actually get a map from S to the moduli space, a morphism. So what this says is not only do the points of your moduli space parameterize the right objects, it also says that if you have a family of sheaves, it will give you, parameterized by some base S, it will actually give you a map to the moduli space. So the technical way of saying that is that this is the coarse moduli space of a natural moduli functor. And again, there is a beautiful book by Herberts and Lane that you can study to make this precise. But for this talk, we only need to know that we have some scheme, it's compact, and its points are the right objects. They're the sheaves on the variety X. So are there any questions? So if not, let's continue. So I want to talk a little bit about the dimensions of the moduli space and a few properties. So if you have a point in your moduli space, okay, so that's some torsion-free sheaf, stable, churn character V. You can ask, what is the tangent space to the moduli space, the Zariski tangent space? And it's the first extension group of F with itself. And if F happens to be a vector bundle, this is the first cohomology group of the endomorphism sheaf of F. Now in Herberts and Lane, if you have a coherent sheaf F, they define a trace map from the ith extension group of FF to the ith cohomology group of O. And let's denote the kernel of this trace map by xi trace 3. And let's write by small xi the dimension of this X group, this trace 3 X group. So then, if it happens that the first Betti number of your variety is 0, well, first of all, then the trace free X1 is the same as X1, so there's no difference. And then there is a very nice dimension estimate for your moduli space. So the dimension of your moduli space at a point F, it lies somewhere between the first trace free X and the first minus the second trace free X. So in general, these moduli spaces are highly singular and very complicated, and we usually don't know their dimension, but at least we know it sits somewhere in between this range. And actually this lowest number is a lot better behaved. It's it turns out that this difference here between these two x groups is something we call the virtual dimension, and it only depends on the Chern character v. I should say, I forgot to say write one thing here. This fact that this virtual dimension is a topological number, so only depending on v, that actually assumes that x is two-dimensional, which we'll be looking at anyway in a minute. But I mean, so far this slide is general, but this last statement only depends on v. That is actually only true if you assume x a surface or a curve. So this, okay, that has to be written here. So then already you can, if you know the Riemann-Roch formula in the appendix of Hartshorne, then in the two-dimensional case for a Chern character of this form, you can actually calculate this virtual dimension. And it's the following number. It's 2rc2 minus r minus 1 c1 squared minus r squared minus 1 times the holomorphic Euler characteristic of x. So yeah, this is a very important number. And you should think of this as the expected dimension of your moduli space. So now we want to calculate some things. So we now really focus on projective surfaces, some very ample divisor, some Chern character, some rank R, C1, C2. And we always assume this condition, the greatest common divisor of R and C1 H is 1. I didn't really motivate this. The point is that if you don't assume this, unfortunately, your moduli space is still not projective. And you have to add objects called semi-stable sheaves. But semi-stable sheaves are much more complicated because they are not simple. So I don't want to get into this. So this is a numerical condition we really want. Okay, yeah, so some surface, some ample divisor, some Chern character, and this numerical condition. So let's rewrite this moduli space MXHV as MXHRC1C2. So it depends on the rank, a first Chern class and a second Chern class. And the second Chern class lies in the highest cohomology group. So that is really, if you like, by Poincare duality, it is set. So now we finally start getting to some numbers. We want to define a generating function. So we fix the surface, the polarization, which we needed to define stability. We fix the rank and we fix the first Chern class. But we want to sum over all second Chern classes. And we want to look at the Euler characteristic, the topological Euler characteristic of these moduli spaces, where Q is a formal variable keeping track of C2. So first of all, one observation you can make is that this is a Laurent series. So if C2 becomes very small, these moduli spaces become empty. And that's actually a consequence of a famous inequality by Bogomolov. If you have a stable sheaf of rank R and Chern classes C1, C2, then this combination 2rc2 minus r minus 1 c1 squared has to be non-negative. So this tells you that, yeah, for stable sheaves, if we fix R and C1, if you take C2 sufficiently negative, you violate this inequality, so the moduli spaces become empty. So that tells you it's actually a Laurent series. So yeah, as I mentioned in the break briefly, the reason this is interesting for physics is, well, first of all, Yang-Mills theory is something interesting in physics. I mean, for instance, the standard model is a Yang-Mills theory. But then if you look at something called N is 4 supersymmetric Yang-Mills theory, so Yang-Mills theory with the maximal number of supersymmetries, if you look at this on a 4 manifold, Vafa-Witten discovered a topological twist. And in this topological twist, the path integrals of your theory, they really become this generating function. And then it's particularly interesting if you do this on a 4 manifold, which underlies a complex algebraic surface X. For instance, the projective plane, it's a complex algebraic surface, and it has an underlying real 4 manifold. So yeah, these generating functions are really topological incarnations of path integrals. So we want to calculate them. So now I'm going to tell you something about the structure of these generating functions. So if we have a surface, let's just stick to surfaces in P3. And let's say the degree of your surface is D. Then in some sense, there are three cases. The case where D is 1, 2, or 3. So those are called del Pezzo surfaces. It means that the anti-canonical divisor is very ample. Then there's these four. These are called K3 surfaces. They're like Calabi-Yau threefolds. They have trivial canonical bundle and trivial first Betti number. And then for D bigger than 4, your X is of general type. So by definition, you say that your surface is of general type. So this is the rest in some sense. Now already with what we know, the little we know about moduli spaces, we can say quite a few interesting things. So if X is a del Pezzo surface and F is a stable sheaf, first of all, you can prove, this is not too hard, that F tensor, the canonical bundle, is also stable, but the slope has decreased. And then by the previous exercise, okay, so let's do two things. We look at the X2 of FF, the second extension group. Then by Serre duality, this is Hom of F tensor, the canonical bundle. But we saw in the previous exercise that you cannot have a map from a stable sheaf to a stable sheaf with a smaller slope. So all of these X2s are 0. And this is very important. If we plug this in this dimension inequality here, we see that these X2s here vanish, even before taking trace. So we see that these equalities become sharp. The dimension is just the dimension of the tangent space. So that means if you have a space where the dimension is everywhere equal to the dimension of the tangent space, you have essentially proved that your moduli space is smooth and the dimension is equal to this virtual dimension. So in these cases, these del Pezzo cases, these moduli spaces are really smooth projective varieties with a known dimension. And we want to know their Euler characteristic. And in the K3 case, it's also the case. So here, the argument is slightly different. You look at X2 of FF, it's actually slightly easier. So this is Hom of FF dual, because the canonical bundle is trivial. But then we take out the trace. So this is C, because a stable sheaf is simple. But we take out the trace, so then we get 0. And then by the same reason, you get a smooth moduli space of expected dimension. But then for general type surfaces, all hell breaks loose. These things become singular, and they may have several irreducible components with all kinds of scheme structure, and usually we don't even know their dimension. Okay, so now let's talk about the rank 1 case, which is closely related to Lothar Goetsche's lecture yesterday. So let X be a smooth projective surface, and I do want the first Betti number to be 0. So a rank 1 torsion-free sheaf on a smooth projective surface is somewhat harmless. So first of all, we saw stability is automatic, but you can also show that they are always an ideal sheaf of a zero-dimensional subscheme tensored by a line bundle. So L here is a line bundle, and IZ is the ideal sheaf of a zero-dimensional subscheme. Actually, and the Chern character you can then also calculate quite nicely with the calculus of Chern characters that we discussed. It becomes the Chern character of the line bundle minus n times the class of a point. So point here is the Poincaré dual of the class of a point in H4 of X, the singular homology in degree 4. So n here is just the dimension of the global sections of your zero-dimensional scheme. So generically, Z will be just n distinct points lying in your variety. So this is the Chern character. So actually, this fact can be proved, this fact that every rank 1 sheaf is of this form, by using that fact that I stated earlier, that the quotient of F double dual by F is a zero-dimensional sheaf. And if you then also use the Chern of OZ is n times a point, you can prove all of these facts here. So then there exists a projective scheme called the Hilbert scheme of points. on your surface. So yesterday you saw Hilbert schemes of points on a curve. There's a Hilbert scheme of points on the surface. And it has the following properties. The points in here are just the zero-dimensional closed subschemes, where the dimension of the sheaf of functions is n. So generically, these are n distinct points, but they're allowed to come together. And again, there's a family statement, but let me not go into that. So if you have a family of zero-dimensional closed subschemes over base S, you actually get a map into the moduli space. So this is a result due to Grothendieck. So the precise formulation is this Hilbert scheme is a fine moduli space for some natural moduli functor. It's better actually than these moduli spaces of sheaves, which are only coarse moduli spaces. So already there's a nice exercise you can make. The map from a zero-dimensional scheme to its ideal sheaf. It gives you a bijection from the Hilbert scheme to the moduli space of sheaves for this Chern character. So a rank 1 space, moduli space of sheaves is just a Hilbert scheme. So far it wasn't transparent why I assume this first Betti number equal to 0. So this is actually what you need for this bijection. Because in general, if you don't assume this, there's still this line bundle L with first Chern class 0. So that can then also vary, but if you assume C1 is 0 and the first Betti number is 0, this L you tensor by is just O. So then this really becomes a bijection. And this is not just a bijection between sets. You can actually prove that this is an isomorphism of schemes. So in this rank 1 case, the moduli space of sheaves, which in character 1, 0, minus n, really is the Hilbert scheme. So there are a few nice facts. This Hilbert scheme is connected, result by Fogarty, and it's smooth, of dimension 2n. So for smoothness, let me give a sketch of how you show this. So smoothness of the Hilbert scheme, you want that this trace map is an isomorphism, because if that's the case, then after taking out the trace, well, if this is an isomorphism, if you take the kernel of this, it means the x2 trace free. So sorry, after taking the kernel of this, you get 0. And then again, you go to this dimension inequality and you get smoothness. So then it turns out this isomorphism is just Serre dual to the map from global sections of the canonical bundle to morphisms from the ideal sheaves to the ideal sheaf tensor canonical bundle, where the map is just composing with the section. So if you show that this natural map here is an isomorphism, you're done. And then here in this exercise, I give a sketch how you can actually show that this map is an isomorphism. So yeah, this involves manipulating cohomology groups and X groups. Okay, so now we go to our first generating function, rank 1 C1 equal to 0. And in this case, everything is independent of stability. So we may just pick any h because there is no stability to check. So let's then just call this generating function that we looked at earlier, gx Oi for Euler of Q. So now it just becomes the generating function of Euler characteristics of the Hilbert schemes. So can we calculate this? Well, with the machinery that we have developed so far, even in its simplest case, we can already calculate this generating function. Let's go to P2. So P2 has this torus action. So this torus action lifts to the Hilbert scheme. So if you have an ideal sheaf and you have a point T in your torus, you can just pull it back along the action by T. This gives a T action on the Hilbert scheme. So then by the general rules of calculations for Euler characteristics, the generating function is just the generating function of the fixed points of these Hilbert schemes. But now we can use our toric description to classify what these fixed points are. So a rank 1 T equivariant torsion-free sheaf, I, together with an inclusion into the structure sheaf such that the co-kernel is a zero-dimensional closed subscheme of dimension n. Those are precisely the points in the fixed locus. So in other words, in each chart, we just have to specify an ideal sheaf inside of the structure sheaf. And it has to be T equivariant. But we precisely know what rank 1 T equivariant torsion-free sheaves look like. We understand what it looks like when they lie in their double dual. So we can really classify these fixed points. So it boils down to, in each chart, specifying a monomial ideal. So in each chart, O is just the polynomial ring in two variables, Cxy. And this inclusion is just a monomial ideal I lying in Cxi. And the co-length of, so the length of this quotient, so yeah, in each of the three charts, you get a monomial ideal of some co-length, and those co-lengths have to add up to n. So the generating function is nothing but counting how many monomial ideals there are in the polynomial ring in two variables, where the co-kernel has dimension n. So this is a purely combinatorial problem. You can show that this is the same. So this generating function of numbers of monomial ideals with co-length n, it's just the sum over all Young diagrams, where you sum over the size. So maybe here maybe I should draw a picture. And so we're looking at the C of xy, and we draw a monomial ideal in there. So an example of a monomial ideal is something like x squared, xy, y squared, let's say. So that looks like this. We have a generator. Okay, so yeah, so we have lattice points. So in terms of our toric description, this ideal sheaf, it really just means we put C on all of these lattice points in this region. Everywhere. And everywhere else outside of this shape, we put 0 everywhere on the lattice points. So 0, 0, 0. And the maps here, I mean, there's only one inclusion you can have between C and C, which is the identity. So all of the linear maps here are just identities. So really what you see is, and this partition here, so you're just looking at, so what is the ring of functions in this particular case? So Cxy modulo I. It's just, well, you mod out by x squared, xy, and y squared. So as a vector space, it's just C, direct sum C times x, direct sum C times y. It's this point, this point, and this point. So, and the dimension of this vector space we can count, the dimension is 1, 2, 3. So here I have an ideal, a monomial ideal. In the polynomial ring in two variables. The ring of functions, which is the quotient of the scheme defined by this ideal, is three-dimensional. And we also see from the picture that this monomial ideal corresponds to this Young diagram. So in some sense, I'm just drawing the elements that are generating the ring of functions. So in this sense, you get a bijection between monomial ideals and Young diagrams. So really, now your generating function is a purely combinatorial. So you have this in each of the three charts. So you just have to look at this generating function of Young diagrams and do it to the power 3 for each of the 3 charts. So then actually Euler already solved that problem. So this is a nice combinatorial problem. It's a bit tricky, but you don't need any advanced tools. So yeah, this formula turns out to be the case. So the generating function of these Euler numbers, it's just this pretty infinite product formula by Euler. So now we have calculated our first generating function. So let's call this 1 over eta bar of q. This is the normalized Dedekind eta function. So this is just notation. So we have proved that the generating function of rank 1 torsion-free sheaves on P2 is this eta bar to the power -3. So this is our first generating function. So now as an exercise, you can do this for P1 cross P1. You have 1 chart more in this case, so the 3 becomes a 4. So now let's go to an arbitrary. So here we very heavily relied on first going to the fixed point locus, and there we have a description in terms of linear algebra data of our sheaves. So this fixed point locus consists of finitely many points, and we just count them. It's these monomial ideals. But now on other surfaces, this was actually one of Daniel's questions. What do we do if we don't have, do we always have this torus action? Well, no, but there are cases, as we discussed, where this doesn't happen. So can you still calculate these Euler characteristics? So now let X be an arbitrary smooth projective surface. And actually for this part, I don't need the first Betti number to be 0. So let me give a few slides on an interesting theorem that I just will state as a fact, but it's very satisfying. So if we have, let's define for each n, Pn, to be a polynomial expression in Chern classes of the tangent bundle of the Hilbert scheme. And let's say that polynomial has total degree 2n, where I say the ith Chern class of the tangent bundle has degree 2i. So T here is the tangent bundle, the holomorphic tangent bundle to the Hilbert scheme. And let's say P0 is 1. And let's just consider what happens if we integrate, right? So Pn is some polynomial in Chern classes. So these are, you can view these as differential forms. So we can integrate them over this, right? They lie in H, in H upper to something. So if they have the right degree, we can integrate them over this compact manifold and put them in a generating function. Let's call that g of p. So now for the moment we leave the Euler characteristic world. Well, as an example, if you want to recover Euler characteristics, an example is the Euler characteristic of a smooth complex manifold of dimension d. It's just the integral of the top Chern class of the holomorphic tangent bundle. You may also just integrate the total Chern class, because all the lower Chern classes have the wrong degree. So if you integrate them, I mean, if you integrate the 1 form on a 2 manifold, you get 0. So you may put them all in. And yeah, so then you could take as an example, you could take Pn to be the total Chern class of the tangent bundle. So that's an example. But this what I'm going to tell is much more general. And let's relax a little bit what we mean by surface. We allow our surface to be disconnected. So our surface is allowed to be disjoint, say, for example, 2 disjoint copies of P2. Now, if you have the Hilbert scheme on a disconnected surface with 2 components, it just means you distribute your points over the 2 disconnected components in such a way that the total sum is n. So then Hilbert schemes still make sense. These integrals you can still compute. So now let's put an important condition on our Pn's. Let's say if we have indeed a disconnected surface, well, copy x1 as a generating function, copy x2 as a generating function. And let's just assume if we have x is the union of x1 and x2, let's assume P has the property that the generating function on x is the product of the generating functions on x1 and x2. So this is actually the case for Euler characteristics. So there, ultimately, it will go back to one of the properties I listed for Chern classes, namely in a short exact sequence, the Chern character of the middle term, the Chern class, total Chern class of the middle term is the product of the two outer terms. So using that fact, you can actually prove that for this choice, you have this multiplicative property. And in fact, in this case, you can find there's also topological proof using the rules of calculation with topological Euler characteristics. So in this case, Ellingsrud, Götze, Lane, they proved something very beautiful. They proved if you are in this setting, so you are on a smooth projective surface, you have on each of your Hilbert schemes a polynomial expression Pn in the Chern classes, satisfying this multiplicative property. You're allowing disconnected surfaces here. In that case, Ellingsrud, Götze, Lane, they proved there exists two power series, A and B, formal power series, which only depend on P. They don't depend on X. And they have the following property. For any smooth projective surface X you pick, your generating function is this first formal power series to the power C1 of the tangent bundle squared. So again, I'm implicitly using, that's an element of H upper 4 of X, which is an integer. So this is A to some integer, and then B to the power the second Chern class of Tx, which is actually the topological Euler characteristic. So here, by the way, an is just a formal notation for the exponential of n log of your formal power series. So they say that if you fix P, there will always be two power series that calculate this generating series for all x's at the same time in one go. But this means, now going back to, or even in this general setting still, this means if you want to know this generating function on all surfaces, you only need to find two surfaces where the vector of these two Chern numbers are independent as vectors in Q2. And if you then know what the value of your generating function is on these two surfaces, then you know it for all surfaces. So now we can apply this to Euler characteristics.
Can I ask something?
Yes, please.
So are you still assuming that the moduli space is smooth? Or
yeah, so here we are, that's a good question. So here we are really on the Hilbert scheme, which is the rank 1 case. So rank 1 moduli of sheaves. And so this is really a fact about the Hilbert schemes. And here we saw that the Hilbert scheme of points on a surface is always smooth. So so it needs the smoothness, and it also definitely needs that we are on Hilbert schemes. It's something
because you're doing this integral, so I was like confused.
Yeah, that's right. That's right. These integrals only make sense on smooth spaces. That's right. Actually, the final slide says just in words that there exists something you can do on singular moduli spaces, but this requires a whole bunch of technology. But indeed, this is just a bunch of differential forms that you integrate over a compact manifold. So a bunch of holomorphic differential forms integrated over compact, complex, smooth manifold. Okay, so let's do this for Euler characteristics. Well, we already have two surfaces on which these Chern numbers are independent. If you do this for P2, then C1 squared is 9 and C2 is 3. And for P1 cross P1, C1 squared is 8 and C2 is 4. So those are two Q independent vectors. So then, and we know on those two surfaces, P2 and P1 cross P1, we know what the generating function is. So here some magic really happens. You find, from knowing only these two cases, we find the generating function for all surfaces. So for all smooth projective surfaces, we obtain, it's just the Dedekind eta function to the power minus the Euler characteristic of the surface. So A in this particular example is 1 for Euler characteristics, and B is the inverse of the Dedekind eta function. So this completely solves the rank 1 case. So this is known as Götze's formula. For instance, then you can play a bit. You can say for a smooth projective surface of degree D, I can try to calculate this Euler characteristic. For instance, by using this Hopf index theorem that I stated, right? So for a smooth manifold, it's the top Chern class of the tangent bundle. And if you really want to practice using the calculation rules for Chern classes as stated in Hartshorne Appendix A, you can use that Hopf index theorem to prove that the Euler characteristic of a degree D surface is this number. So this number magically becomes 24 if D is 4. So for the K3 surface, this number in the power here is minus 24. So in that case, the Dedekind eta function to the power 24 up to an overall character becomes what's known as delta of Q. This is the discriminant modular form. So I'm not going to talk about modular forms here, but modular forms are very special holomorphic functions. The precise statement is, this is the Fourier expansion of a holomorphic form. And this already starts connecting to the physics, because what Vafa-Witten predicted is that these path integrals should produce modular forms. This is the very first incarnation where this happens. So I don't think I will do all of the remaining slides, perhaps, but I think I should be able to. Can I have a few more minutes for P2 at least? Because here we really developed all the theory. Because now we want to go up in rank. So we go to rank 2. So let's go to rank. So first, let's see, what do I, oh, okay. So first something general still. Let's go to a smooth projective surface with first Betti number 0. And we fix some Chern character, R, C1, C2. And again, H very ample divisor and this greatest common divisor condition. So inside the locus of all torsion-free sheaves that are stable with these Chern classes, we have the locus of locally free sheaves, because a locally free sheaf is torsion-free. So this turns out to be an open subset. Although it could be empty. Now let's look at the disjoint union of all of these moduli spaces at once. So R and C1 are fixed, but we take the union over all C2. So then we have this nice map. We can turn a torsion-free sheaf into a vector bundle by just taking the double dual. So we map from the union here to the union here. This map needs some fine print. It's unfortunately not a morphism of schemes. It's what's called a constructible morphism. So it means the domain here can be written as a union of locally closed subsets, such that on the locally closed subsets it is a morphism. But this is good enough for Euler characteristic calculations. So we shouldn't worry about it too much. It's just not a morphism. It's a constructible morphism. Now the fiber of this map over a point, over some vector bundle F, is what's called a quad scheme. So said theoretically, it's all possible surjections onto a zero-dimensional co-kernel. And that's because of this, this fact that I stated. The quotient of the double dual of a sheaf by the sheaf is always zero-dimensional. So this double dual map can be used, this map phi can be used to show that actually for Euler characteristics, you don't need to know the Euler characteristics of these m's here. You just need to know the Euler characteristics of these n's, of these moduli spaces of vector bundles. So we don't need to care about torsion-free sheaves anymore. We just need to know the generating function of Euler characteristics of these moduli spaces of vector bundles, no longer locally free sheaves. Although here Daniel's point becomes important. So, first of all, if you would want to do integrals, you better be on smooth compact spaces. But I mentioned that Euler characteristics, they do make sense on non-compact spaces, right? Because I already talked about the Euler characteristic of A1, for instance. And moreover, they don't even need your space to be smooth. So for Euler characteristics, this is fine. It's just that you can't calculate them by the Hopf index theorem. But if you just insist on topological Euler characteristics, this is perfectly well defined. And now, again, we lift the torus action from, so let's say we have an action of c star squared on X, our surface. Then it lifts to the moduli space simply by pulling back your sheaf. Don't worry too much about this inverse. This is just if you're a representation theorist, you would want to put an inverse here, but actually you can also put just T here. So then if you have such a torus action, well, then one of the rules of Euler characteristics is you just need to calculate the Euler characteristics of the fixed point locus. And now, what are the vector bundles that lie in this fixed point locus? Well, there's a general fact. If you have a simple sheaf, it's T fixed, meaning that for every T, T star of F is isomorphic to F, so it's invariant under pulling back along all points of the torus. If and only if your sheaf admits an equivariant structure. But if it is T fixed, so it admits an equivariant structure, the equivariant structure is not unique. So we already saw that the structure sheaf O can have many equivariant structures. So this is only unique up to tensoring by a character, an element of this character group, this copy of set 2. So yeah, so you can almost think of elements in the fixed locus as equivariant sheaves. It's just that you have to remember that there are more than one equivariant structure. And this will actually be beneficial in a minute. So yeah, actually at the fixed point level, you can prove this formula that's written here on the top by using the descriptions in terms of linear algebra data. So for rank 2 on P2, this is a nice exercise. It's not trivial, but yeah. Okay, so now we come to the main point of the lecture. So now we're going to calculate a rank 2 generating function. So we're on P2. We fix the polarization and the first Chern class to be the class of a line on P2. We take the rank equal to 2, and we want to calculate the generating function of these Euler characteristic of vector bundles. Okay, so first we have a toric description of these vector bundles. As we saw in the first part of the lecture, they are parameterized by, well, rank 2 vector bundles. In each of the 3 charts, you need to specify 2 flags of C2, rank is 2. But because of the gluing conditions, you only have to specify 3 flags. So if we want to sum over all of those vector bundles, all of those T equivariant vector bundles, we sum up over all ABC, delta 1, delta 2, delta 3. So let me, okay. Okay, and also V1, V2, V3. So I forgot to write one thing, but let me comment on this in a minute. So also V1, V2, V3, they are one-dimensional subspaces of C2, mutually distinct. And we need the following conditions. So first of all, we can put A and B equal to 0. And this has to do with the fact that the T equivariant structure is unique up to tensoring by a character. That means in one chart, we're allowed to specify A and B to be equal to any value we like, let's say 0. So A and B are fixed. Okay, so and then we want to fix the first Chern class. So this should say T, C. So 2C plus delta 1 plus delta 2 plus delta 3 is -1. So this is this first Chern class formula that I wrote all the way in the beginning. Or actually the complete Chern character. In the beginning somewhere I gave you the formula for the Chern character of a rank 2 vector bundle. So that's this formula here. So this little part here, we want to be equal to H, right? So you get -2 A plus B plus C plus delta 1 plus delta 2 plus delta 3 is equal to 1. Except that I at first I want to put B and C equal to 0. Later I decided to put A and B equal to 0. So actually in this formula there's a small typo, right? So I should be putting C equal to 0 here. So also we want our sheaf to be stable, and that we already saw is encoded by these triangle inequalities. This is stability. So what I didn't write here is we're also allowed to vary V1, V2, V3 over all possible subspaces of C2. So you should think of these as 3 points on a P1, and they're allowed to vary in whatever way we like. But they have to be mutually distinct, because we already saw if two of them collide, if they become the same, the sheaf is no longer stable. But one thing that I forgot to write on this slide is we only look at sheaves up to isomorphism. And what that means is, you may know the automorphism group of P1 is PGL2. So classically, any 3 points, if you have two sets of 3 points on P1, there's always an action on an automorphism of P1 which maps them to each other. So if you look at sheaves up to isomorphism, these V1, V2, V3, you can fix them as long as they're mutually distinct. So yeah, so any 3 distinct points on P1, you can always map them to, let's say, 0, 1, 1, 0, 1, 1. So there is no moduli left there either. And what do we sum? Well, we sum Q to the power C2. So if you go back to this horrible formula that I showed earlier, it's just this. If V1, V2, V3 are mutually distinct. So really, the generating function is just the sum over all this data here. So C here we can solve for, right? It just that's it here. This here, you just need that 2 divides this sum here. So you get this sum, and it's Q to this power. So this is really the answer. This is a very beautiful answer. And so first of all, it's very interesting to try to manipulate this formula a bit. You can write it much easier in this shape. This is actually not super hard, but it's a bit of work. So the conclusion is really we have calculated this generating function in the rank 2 case. It's this power of eta that we took out by taking double duals times this function here. So we get a very compact thing. So this is a very beautiful object. It turns out that this is also the generating function of objects studied a long time ago, so-called Hurwitz class numbers. And Don Zagier studied this function. It turns out to be the holomorphic part of what's known as a mock modular form of some weight. So I won't explain what that is, but for people excited about holomorphic forms, this is holomorphic modular forms. This is a mock modular form. Mock modular forms themselves are among modular forms. They're not modular forms, but closely related, and they're very interesting, related to the work that Ramanujan did at the very end of his life. And the fact that this is mock modular has to do with something called holomorphic anomaly in Yang-Mills theory. So also from the physics point of view, this formula was used by Vafa and Witten to really say interesting things about Yang-Mills theory on P2. Okay, so yeah, we have now seen that on surfaces with a torus action, we can really use the linear algebra description of T equivariant sheaves to calculate these generating functions, at least for P2. And again, it's very nice to, well, if you study, for instance, moduli of sheaves from this beautiful book, it's very nice to also keep in mind what happens in very concrete examples like P2. What does stability mean on an equivariant sheaf on P2? And then sheaves really become linear algebraic objects, stability become really linear algebraic conditions on that data. So it becomes very concrete. But I also want to give you some flavor what happens beyond the toric case, beyond the projective plane, let's say. So in this trichotomy, we had surfaces of degree 1, 2, 3, 4, and 5 and higher. So 4 is a very curious case. This is the case of K3 surfaces. So now let's say we're on a K3 surface. Just think of a degree 4 surface in P3. And we fix rank C1 and C2. And again, a very ample divisor and some coprimality condition, because otherwise our moduli space may not be compact. Then there's a very pleasant fact due to O'Grady and then later generalized by Goethe and Algebraic and generalized further by Yoshioka, we already saw that whatever this moduli space is, it's smooth. That we already knew, and it has its expected dimension. That was this x2 calculation that we did using Serre duality. But it turns out that in this case, it's actually deformation equivalent to the Hilbert scheme of points of the same dimension. That means if you change the complex structure on this moduli space, it becomes a Hilbert scheme. So topologically, it's the same as the Hilbert scheme. The Hilbert scheme where n is chosen so that it matches the dimension of the moduli space of sheaves. So they are not literally Hilbert schemes, but they are Hilbert schemes after you change the complex structure. So topologically, they are the same as Hilbert schemes. So that just means the Euler characteristics is just, we already calculated in terms of this discriminant modular form. So, and then you can, if you like, you can actually, I mean, even if you have this purely at the computational level, you may want to put this into a nice generating function. So if R is a prime number bigger than 2, and you take an rth primitive root of unity, you can actually sum these Euler characteristics up into a closed generating series. So the reason this looks complicated is, like, the point is this, that you have this n is related to C2 like this, and C1. So we fix R and C1. So it's not true that the generating function is this discriminant modular form, because you see here, there's 2rc2 written here. So, and in this generating function, we sum over q to the power c2. So we don't pick out, we don't see all the terms in the Hilbert scheme. We skip some terms in this generating function here. So yeah, so there's some congruence conditions. And here there's a little exercise showing that, well, if I have some generating function and I only want to extract the coefficients which are, let's say, congruent k modulo r, there's some nice way of doing this. And then you get this formula. So this solves completely the K3 case, at least in prime rank. And even for any prime rank. So here we did much more than rank 2. So in this sense, we really get a nice answer for K3 surfaces. So I will end by general type. So here I will only sketch, just give you a flavor, because this is very close to current research. Actually, even all those other cases, K3 and P2, for instance, P2, if you go beyond rank 2, also you already enter current research. So all of these topics are very close to, are immediately bringing you into current research. So for general type, so let's take a smooth projective surface with first Betti number 0. And let's say your surface has a holomorphic 2 form. So it has a holomorphic 2 form. So surfaces of degree 5 and higher in P3, they have this property. So we fix some rank, first Chern class, second Chern class, ample divisor, this coprimality condition. So as I said before, okay, these spaces become very singular in the general type regime. They may have many irreducible components. We usually don't know the dimension. And you can calculate the Euler, well, you can't do it in practice, but the Euler characteristic of these spaces is a well-defined object. Space doesn't have to be smooth for that. But it's not the wrong type, it's not the right type of thing to look at. So it turns out there is a notion of virtual Euler characteristic due to Van Tecke and Goethe. So if we call this space M for the moment, it's actually, if M were smooth, we have this Hopf index theorem. It's just the top Chern class of the holomorphic tangent bundle. But this formula doesn't make sense, as Daniel also pointed out already, if M is singular. So in the singular case, there's a sort of what's called virtual analog of this formula. So you need to replace the fundamental class by what's called the virtual fundamental class. and the tangent bundle by what is the virtual tangent bundle. So I'm not going to explain what these objects are. I mean, that's a whole series of lectures on its own. But let me just say a few properties. Whatever this virtual fundamental class is, it lives in the right degree. So even if M has a very high dimension, and we don't know the dimension, or there may be components of several dimensions. Remember, we had this x1 minus x2, this topological number, which we call the virtual dimension, the expected dimension. Well, this virtual fundamental class lies just in homology of the expected dimension. So even though this moduli space may be horrible, there exists a class which behaves as though this moduli space is smooth of expected dimension. So this virtual fundamental class was constructed in great generality by Berend van Tecky, and it's also an object you encounter if you study Gromov-Witten or Donaldson-Thomas theory. I mean, I saw that you will also get lectures from Yalong Zhao, and he will also probably talk about some virtual classes at some point. But yeah, you should think of it as a replacement of the fundamental class in the smooth case. And I can say a little more about this virtual tangent bundle. So this replaces the tangent bundle, which you have in the smooth case. I mean, on a singular space, there's a tangent sheaf, but not a tangent bundle. This thing is not a sheaf anymore. It's actually a complex of sheaves. But whatever it is, it has some very nice cohomology. So if you restrict this virtual tangent bundle to a point, and you take cohomology, there are only two cohomologies. There's a cohomology in degree 0, which is this first extension group, which is the tangent space of the moduli space. And there's a second cohomology group. And then all the other cohomology groups vanish. So yeah, these are the two replacements that you have to make. And there's even a tool to calculate such Euler characteristics, something called Mochizuki's formula. And this allows you to reduce from rank R to rank 1. So he has an explicit formula which reduces these, well, actually very general intersection numbers, but in general also, specifically also these Euler characteristics, to just what's called Seiberg-Witten invariance and some integrals on Hilbert schemes. And those integrals on Hilbert schemes you can study again with techniques like the Ellingsrud-Goetschel-Lane theorem that I mentioned. So using this, if you have a surface as before, so first Betti number 0, it must have a holomorphic 2 form. So if we have such a surface and we assume it's minimal of general type, so you may just think of a degree 5 surface in P3, degree 5 or higher, then using all this technology that I only mentioned, didn't explain, you can actually also calculate the generating function in the rank 2 case. Well, I should say calculate, you can, in specific examples, it turns out this Mochizuki formula is not strong enough to calculate the general case. You can only go to a specific minimal type surface, minimal general type surface, and then calculate these generating functions up to some order. And then from those calculations, you see a pattern emerging. So there's some formula. It looks a little bit like, the first part looks a little bit like the K3 case. So here I'm only talking about rank 2, some overall factor. There's some square root of -1. There's some Dedekind eta function. This is all a bit similar to before. But then here there's something new happening. There's a Jacobi theta function coming in. I mean, the precise shape is not so important. All you have to see is that it's explicit and it involves sort of modular objects. And again, let's make some remarks. This is not a theorem, but this has been verified for a whole list of surfaces up to some order in Q using Mochizuki's formula. And what's very curious is this formula actually appears in Vafa-Witten's 1994 paper on S-duality. So they, at the end of their paper, so this paper is about certain path integrals on NS4 supersymmetric Yang-Mills theory on which you perform a topological twist. And at the end of their paper, they do some purely physical calculations using superconducting cosmic strings. And the calculation is purely physical. And then, more than 2 decades later, mathematicians were able to define what they are calculating, namely virtual Euler characteristics. Note that these virtual Euler characteristics didn't appear in the literature yet when Vafa-Witten did their calculation. And we can really see that the formula that they get matches this formula. So we really prove that we give meaning to that formula geometrically and verify it up to some order in specific examples. And again, it's the route is so different. They use purely physical objects, whereas here you use algebraic geometry. And actually, it turns out using this machinery, we can do some higher ranks too, 3, 4, and 5. And in 5, you get very interesting modular forms coming in, namely the Rogers-Ramanujan continued fraction. But I should also say, in this setting for general type surfaces or surfaces with holomorphic 2 forms, the moduli space that I've been talking about, stable torsion-free sheaves, is not the right moduli space actually. And also this is not the complete answer. So Tanaka Thomas, they say you need to, they have a paper from 2018 where they say you should go to a bigger moduli space called a moduli space of Higgs pairs. And roughly speaking, this moduli space, it sits in there, but it's not the entire moduli space. And likewise, indeed, if you go to Vafa-Witten's paper, they're generating functions on these superconducting cosmic strings. They involve this factor, but it's not everything. They have a second term. And that second term is explained by Tanaka Thomas's theory. So you also need to enlarge your moduli space. And then you get into a very interesting topic called S-duality, which I won't talk about, but it's now something that you can mathematically approach using all this technology. So this last section on general type is really just to give you a flavor. So yes, again, you can zoom in on some of these topics. Once you digested parts of Hartshorne, you can really zoom in on all these various facts that I mentioned in this talk. And things like torsion-free sheaves on P2, they're really concrete objects. So here there's a list of, the first references are sort of what you need to do everything up to P2. And then there's some more advanced reading where some of the background physics is discussed and what happens on K3 surfaces. And of course, this is a small selection of a much larger literature. And again, also in this book, there is a lot of literature. So it's a very big topic, but this is just to give you some flavor of the subject. Okay, that's all I wanted to say. Thank you very much.